Simon Crosby, CTO of Swim.ai. Welcome to the Data Exchange Podcast.
Thanks, Ben. It's good to be here.
And for our listeners, actually, Simon is let's say, one of the most seasoned technologists that we've had on the show. I mean, he was part of Sensors.
That's right.
Was
back when hypervisors were cool.
Yes. Yeah. And also was on the faculty at Cambridge University. So he's also had his hand into academia and research, but for many years has been mostly focused on industrial research and application. So for today, I want to talk to Simon about, I guess, what we would call continuous intelligence. Is that the term you folks use?
Yeah, it's what we use. Yeah, I think it's kind of cool because it indicates a use case, which is really interesting. So real time.
And so I guess for listeners out there, so Simon, they're familiar with things like real time, machine learning.
So wait up.
Streaming.
Real time, I've discovered just means faster than the last time.
Yeah. Or people who are listening to the show are familiar with streaming, machine learning, analytics. So when you folks, so before we talk about the technology, let's talk about the applications and what the technology makes possible. So when you talk about continuous intelligence, what are some use cases?
So maybe there are three kinds of data or data management. The first, say, just SQL, all database stuff, right? Then there was big data,
right?
And now every single process, every single product, every bit of infrastructure is instrumented, and it's generating events. And these events are not traditional transactions.
So this is like starts getting into what people used to call the Internet of Things, but
yes.
Not necessarily just sensors, but even just
it's everything.
IT systems, right?
Right. I mean, our largest user is a carrier, right? And we are processing 4 petabytes a day. Okay.
That's so let me stop you there. So processing, streaming data. So people in, I guess kind of circa 2017, 2018, people have been doing this with other tools like maybe Kafka or something, or Pulsar or things like that. So what is different now?
Cool. So they weren't. First up, you can't store and then analyze. Okay? And everything that we have today, including Kafka and Pulsar, is store and then analyze. You cannot afford to store 4 petabytes a day. That's several exabytes per year. Good luck. Okay, you just can't do it. So what you have to do is continuously analyze, learn, and predict on the fly. And do you want to keep the raw data? Probably not.
So if you're analyzing data that's arriving now, then that's by definition that's not going to be as much data as exabytes. So then,
so wait up. That's 10 gigabytes per second, continuous, every second of every day. Okay, it's a ton.
So is this something, Simon? Is this something that's for most IT shops? It's not actually.
No.
I mean, so this is more the province of really big.
No, it's not.
Okay.
It's not. So the problem is this: is that the next generation of IT systems have to stay in sync with the real world. And when I say in sync, I mean you need to be able to drive a robot. Or when you look at your Uber, you really want to know the car that you're tracking is in front of you and not several minutes away, right? So everything that relies on events relies on timeliness. The user demands timeliness. So real-time, analytics, it's like, yeah, whatever. Anybody can draw a cool graph on the screen that shows stuff. That's the sole problem. The problem that we face is that for any scale, applications have to stay in sync with the world. I hate to draw this analogy, but in the Zuckerberg metaverse notion, right? If Zuck's avatar is out of sync with his speech, it's really bad. I mean, it's bad to stop it, but it's really bad if the avatar is out, okay? And so if you just take that as an analogy, the future of applications is thus. They have to stay in sync with the real world because they control and learn and predict from the real world, and they automate the response.
So,
And that's scale independent. It just turns out that scale is a good way of showing it.
so just to clarify, so when you say in sync, so in sync with what's happening now, so
Yeah, I mean,
you're not as concerned with comparing, let's say, what's happening right now to what happened 1 year ago.
correct.
Okay. Okay. So, but what you're saying is
But
just,
I am really concerned about saying you're near to me now.
but what you're saying is just even if you just restrict yourself to events that are in right now or in the recent past, the volume has grown even more than
The
most
volume is
people think.
high. The volume is high, but more than that, I need to do interesting things, like say you are near me, or the engine temperature is rising and the wheels have stopped, or something like that, right? So correlations,
Or
juxtapositions,
predictions.
or predictions, anything, and they're all related in time.
So why so Simon, why don't the normal scale out approaches work?
The moment you store stuff, you're done. I mean, think about it this way, Ben. The moment you reach out to a database of any sort, you're going 1,000,000 times slower than the CPU.
But
Okay?
when you can scale out and you can combine all the RAM in your cluster
Yes,
and
yes.
yeah.
So the key thing is just move into memory. That's a great first start. But then why use for analysis a paradigm which is store and then analyze? So traditional database style access to data requires that you analyze data after it has been stored in some way, right? And the approach we adopt, which is an extension of the actor model, is that when data arrives, you analyze it
So
as it happens. So it's data-driven compute.
what about Simon these messaging systems like Kafka and Pulsar? Do they suffer
Kafka
from
and
this?
Pulsar are great for dealing with events. All they ever do is queue your events by topic. Goodie.
So
That's useful, but it doesn't analyze the data. They can't find relationships between sources of data, between topics, say, and they don't implement applications. What Swim does, and I'm getting very specific, is we build the analysis of the data as a data flow graph in real time using the data. So as data arrives, we create little actors. Swim is, by the way, from an application developer perspective, it's just Java. But the actors are effectively Java objects that are concurrent, and they continuously analyze, learn, and predict on the fly, right? So for every single source in data, we have an actor. It's a concurrent process. It's stable. It's somewhere in memory. And actors continuously analyze their own data, and they look out for, they continuously execute complex parametric functions to find relationships with others, right? Near, correlated to, or whatever. And they build a graph. So this is like a kind of like Neo4j built from data, right?
So this is so it's interesting because besides Swim, so there's Akka, and Ray is also doing Ray is also doing kind of this distributed actors. But so I guess going back to this messaging systems, they seem to have kind of a SQL interface now.
Yeah.
Right. So,
and I don't blame them. I mean, it's a very powerful interface. It's well known by developers, but my God, it's expensive computationally, and it's not capable of solving really hard analytical problems like learn and predict or find correlations and so on. So these are hard problems.
So you're basically saying, Simon, that in the future, if you want to do predictive models or machine learning on real-time events, on making sure that your system is in sync with the real world, you have no choice but to use this approach.
Yes, you have to analyze, learn, and predict on the fly. You can't afford to store and then analyze. You just cannot do it.
And so when you go in and explain this to people, is it a hard sell, or do they get it right? Did they get it right away?
People are easy to impress. So if I tell you that by moving all computation and adopting this actor-based model, the speed comparison is this. It's the comparison between the speed of a snail and an F-16. Okay, I can impress you pretty easily. And by the way, that's just Moore's law. Okay, the CPU and memory are 1,000,000 times faster than your database. So it's easy to impress people, and people naturally understand the actor abstraction. The problem has been that there hasn't been a good actor implementation. I mean, Akka, I think, is very successful, and I love what those guys are doing.
Yeah.
But most people, at best, know Erlang, right?
Yeah.
From high school or from college.
And now Ray is.
Now Ray is going the way. It's very exciting. So, in general, I think the actor paradigm is about to see a huge refresh. By the way, there's another really important reason. Once we adopt it, we can get rid of a lot of the ops concerns of DevOps. Okay.
So before you go there, let me ask you this. So you're saying that regular developers have no problem with the actor model? I mean, that there's not much of a learning curve for them?
Once they get their heads around it, it's really easy. But getting them to do it, it's a little bit of work. Luckily, most of them have encountered Akka. So, it's getting easier.
And so do you think that, so right now, obviously, the goal is to make it even easier and easier, so make the developer tools even more accessible.
Yes,
but do you think that there's also a role for the training programs and
Sure.
CS courses.
Yeah, all of that.
Yeah.
But I mean, I love what Jonas Bodner is doing with the Akka world, right? So getting people to understand that cloud and serverless is a good abstraction, but serverless being stateless is really
Right.
terrible,
Right.
right? So what we really need to do is make serverless. Serverless is the right abstraction, but stateful as opposed to stateless is really huge.
So let me put you on the spot, right? So let's say I have you give a talk or a keynote, right? So and I give you 2 to 3 slides, and in those 2 to 3 slides, you give me examples of this technology and what it made possible, and
Mm-hmm.
and basically uh, we don't have to focus too much on the scale, but on the actual application.
Cool. So I'll start with one which is in a large telco. So I mentioned before, 4 petabytes a day, right? That's just 4,000 laptops or something. So these guys had 400 instances, 400 servers worth of big data per day. And they're down to 40, okay? And that's just Mozilla, it's all in memory. They were at 10 hours for insights. They're down to 10 milliseconds. That's a million.
Define insights in this case. Is it BI
Okay.
charts or?
So they started out with a customer problem of understanding where outages happen in the cell network. Now they're down to 10 milliseconds. They can automatically retune the radios and fix them.
That's a big benefit to the users of the network, right? So
Yeah.
yeah.
And once we've done that, they have a digital twin, effectively an actor, which represents every one of 240 million devices in the network. Okay. And now they can write applications for security. They can automatically call 911 when your car hits another car. They can do things like understand how many people are entering and leaving every building. Okay, so they can sell those insights to building managers. They can sell insights to insurance companies and so on. Okay, let me give you another one. We're deployed in about 20 cities in the US where every single digital twin of every intersection continuously predicts its future behavior. Okay, so it predicts whether it's going to be red light, red, green, or orange for every lane, right? And these insights are continuously streamed into the consumer's Kafka brokers. So Uber can continuously obtain predictions for the future 2 minutes over every intersection, every city. Okay, so what they're doing is optimally routing their vehicles through the city so that they minimize journey times.
And that's only possible because they can make predictions and analyze based on events right now.
Right, and continuously change directions that they feed to the driver, right?
Yeah.
Yeah. And so then we have a ton of others. Some of them are military. We analyze, learn, and predict every every piece of equipment in space and every bit of space junk, and we predict when they're going to collide. So we can look ahead and see where the orbits are going to collide, and we can appropriately warn participants and so on, right? We have a silly example in a manufacturing plant where all the parts are RFID tagged, and it's a long fabrication plant. And so the natural question to us is, do I have the right bits and so on? Actually, we can do better than that. since every tag is seen by lots of readers, the tags, digital twins of tags, can triangulate off readers and show you where they are in 3 space. And then as the bits come together to make a fabricated part, you can start to do really cool things like say, does that wheel substructure contain all the right parts? Okay, so you move from just saying at what rate am I consuming bits and pieces to actually correctly checking that the things that you manufacture have the right pieces in them. Okay.
So by the way, you've used the phrase digital twin a few times, and actually that's quite powerful. Because once you have a digital twin, you can do all sorts of things. Anything,
right?
machine learning, reinforcement learning, all sorts of things. And for most people, actually, just getting to the digital twin is the main project.
Yes, you're right. And so the cool thing here is that we can do that automatically. So it's this. A digital twin is just an actor, okay, somewhere in memory. And one of the cool things that Swim does is that every actor is also on the web. Its API is just a URI, okay? So it's vertically integrated, and you simply call its API, and then it will stream predictions or analysis. Every single state change it makes, it will stream that to you, okay? And so, well, say in the carrier example, we have 240 million digital twins somewhere in memory. But how do you find them? Well, you just have a URI, okay? And more than that, you can create these digital twins automatically from data. All you really need is a schema and events. And every time when you receive events from a new thing, you create an actor. And then every event thereafter, you hand over to the actor and it analyzes its own events.
So what's the implementation path for this technology in terms of so what's the ideal scenario? Is it a company with sensors all over the place that they're already collecting and storing data, but they're unable to analyze before storing, or what's the ideal scenario?
So in my view, it's use case first, and the primary use case is that the application has to stay in sync with the world. Okay, with that manufacturing.
That's increasingly most applications.
Yes, but we use the term real time, but we're really just lying to ourselves, right?
Yeah.
Or at least, human, and putting cool graphs on a dashboard is not my problem. My problem is controlling automated responses, okay? And often those have to be machine times, right? So InSync has a real, I don't want to go in the hard real-time world, but it has a real consequence in terms of the way you control the world, right? The response.
So there's a tie-in with kind of industrial AI and IoT, and I mean
there is, but by the way, this applies to APM too. So if I have 1,000 or 10,000 VMs in AWS, I want to know what their streaming data actually means and respond to it. So if you think about DevOps, APM as in drawing graphs for humans, like your VMs are on fire. Now what's the point? Let's respond to the stuff automatically and respawn it. Okay, so understanding streaming events on the fly from anything is what we do, right?
The hard thing with the APM space is they have so many tools.
I agree. I have no desire to go there.
but areas like manufacturing.
Yes, but the key thing is that IoT and this edge world is
Yeah.
terrible.
Oh, really?
It's terrible as a market. I
Really?
think if you want to buy
Explain.
smarter,
Explain. Yeah,
there is no independent software market for vendors.
I see.
You can get smarter things from Siemens or Schneider or somebody, right? But the customer is used to buying widgets, and widgets can get smarter over time, great. But there isn't a separate software market where I buy
Infrastructure.
a stupid widget and then buy software separately.
Yeah. Yeah. But
It's just horrible.
telco, you mentioned telco, right? So
Mm-hmm.
what about kind of transportation? All
Oh,
these.
any organization which has got lots of things with their assets, applications, infrastructure, you know, at scale is they really care.
Can Simon, can would you say that events could also encompass more complex data, like data from computer vision, video,
Sure,
images, or
sure they
audio, or
could.
whatever? Yeah.
Yeah, we haven't done anything where we actually have to understand what's in video or audio. I'm assuming that somebody would do that and we would get something out like, the man with the red jumper is in the video, right?
Right.
Um, but we don't actually analyze that kind of data.
Right. So for people who wanna get into this kind of next generation of data infrastructure built around the actor model, so what do you recommend?
Well, you know my world really well. Swim is entirely open source. If you go to swimos.org, there are a
Only
bunch of
so it's only Java right now.
yeah. We're very close to doing our polyglot announcement, and the core of Swim is being redone in Rust.
Okay.
It's very, very cool. So Java right now, and a powerful CLI, so you can do data science on your digital twins using the CLI, and people use Python, for example, for that. But Polyglot soon. Everything in Swim is open source. The platform is there, and several example apps, big ones too. So the carrier app, absent the bit which deals with your cell phone, is all there. Traffic prediction, a bunch of others.
And how does this fit into, let's say I'm a data engineer, how does this fit into the rest of my infrastructure? Let's say I'm already using a bunch of other things like Kafka, Spark, the usual suspects.
So where this model, so continuous intelligence, is about having to continuously analyze, learn, predict, and respond. Okay, and so for applications where storage is fine, go ahead. They're different, right? And that's a traditional infrastructure. So Kafka is fine, and Spark and so on, mostly batch. And what we do is we give you millisecond timescale responses to complex events, events from lots of sources where you're looking for complex answers, right? So you're near me now, or this is correlated to that, or whatever, right? So for those applications where you want to continuously respond to the real world, to your world, this is an approach which is really simple to adopt. It's just the actor model. Programmers already know the languages. We're still in Java. It runs really fast, 1,000,000 times faster than your current app, and continuously predicts, right? And every actor is on the web. So it's just, you subscribe to its API and it'll tell you what every single state change.
And then after I finish responding in real time, which is making the predictions I have to do right now, can I then use that data later for batch analysis?
Sure. And every swim actor is persistent. So everything required to do HA and everything else is there. The way I'd encourage you to think about this is like a database where for every single row update, you're actually going to invoke some code, right? That's the actor doing its own update. But it's all in memory, okay? And it's persistent. Now, across a few hundred servers, a few terabytes worth of RAM is no big deal, okay? That's what used to be your database. Nonetheless, these things continuously persist actor state to stable storage, and they can be highly available.
So you earlier hinted at other programming languages. So are you comfortable hinting more?
Well, Rust is really important for us. So I think Rust is totally awesome from a single instance and embedded perspective. What we want to do is take Rust and make it really the programming language for actors in the cloud. Polyglot support for us also means support for other big cloud languages. Go, Akka is important, and so on. So we'll see. It's all about timing customers.
I see. No Python.
Oh, Python you can do using the CLI already. I mean, maybe you know better than me, but Python in real time, Python in continuous time, right? I haven't seen it. I've seen Python for humans on human time scales, and we already do that.
Right. So let's close. So you mentioned a bunch of examples. So can you elaborate a little more on the sort of analytics and models they use? So just to give our listeners a flavor of how complicated some of these models can be. Are they like machine learning models for predicting events? And so basically you're doing inference, but are you also kind of updating the model in real time or so?
Yeah. So let me describe, if you go to traffic.swim.ai, you'll see downtown Palo Alto. And that's just cool, it's fun. So here's what happens. That's about 4 terabytes today of data off the infrastructure in Palo Alto. So every single in-road loop, every button, every light, and so on. And that's really noisy data. Once you reduce it to the state of the infrastructure, it's vastly less, maybe in through 3 orders of magnitude. And for every single intersection, we create digital twin, and it continuously analyzes, learns, and predicts for every lane and so on. So they're continuously updating themselves, and every cycle, so actually they do it once every second, they take their current state and the state of their neighbors, and that creates a vector, which is probably 1,000 or so elements, and they throw it into a DNN, and out pops a prediction. Okay, if you want, we can deal with time. But the cool thing about this is that when we start up, the DNN is stupid, right? Its edges are random numbers. And so every single one of these events helps learn, right? So we predict something. The first time through, obviously, you're going to get noise. And then you look at the real world and see what really happened take the difference between what you predicted and what really happened and backpropagate. Okay, and if you do that for a few days, hey ho, you get pretty good. And so after a week, every single intersection is really pretty darn good at predicting its own future.
Interesting. Interesting. Well, this has been fascinating, and I hope our listeners check out traffic.swim.ai, but also just swim.ai. Yeah, yeah.
Oh, and swimos.org.
And swimos.org. Thank you, Simon.
Thank you, Ben.